In the previous video, we have been discussing about the syndrome decoding of Hamming codes. Syndrome decoding of, in particular, we were looking at the 7/4 Hamming code, right? Okay, and if you recall, for the decoding part, we use what is called as a parity check matrix, and we multiply the code word with the parity check matrix to get what is called as the syndrome. And by looking at the syndrome, the decoder can decide whether the code word is free of errors, or if it has any error, it will try to correct it, and so on. But before we move on to further examples of the syndrome decoding process, let me also help you recall that the minimum Hamming distance for the Hamming codes, minimum Hamming distance, which we denote as dmin, is equal to 3 in the case of Hamming codes. And with the minimum Hamming distance, we know what is the maximum number of errors the code can detect and correct. So maximum number of errors that can be detected is given by dmin minus 1, which is in this case 3 minus 1, which is equal to 2. So that means a maximum of 2 errors in a code word of length 7 can be detected. If it is more than 2 errors, then there is no guarantee that the 7/4 Hamming code would be able to detect it, because a 3-bit change can result in one code word being converted to another code word. So therefore, the maximum number of errors that can be detected is 2, which is dmin minus 1, and the maximum number of errors that can be corrected is given by the floor of dmin minus 1 by 2. So we take the floor value. So let me write that a bit clearly. So we take the floor value. Floor means the lower integer. We ignore the decimal portion of the answer that we get in this, right? So in the case of the Hamming code, where the minimum distance is 3, that means it is 3 minus 1 by 2, the floor value, which is 2 by 2, which is 1. So that means the maximum number of errors that can be corrected is 1-bit error out of the 7 bits, right? So we have a code word of length 7. Out of the 7 bits, if there is only one error, it can be detected as well as corrected. If there are 2 errors, it can be detected but it cannot be corrected. If there are more than 2 errors in the code word, then there is no guarantee that it will be detected also. Okay, so it may not even get detected that there is an error in the code word. Okay, let us quickly recall what is the code rate of this particular code. Code rate is k by n, which is 4 by 7. Okay, so this is just a quick recap, and let us now proceed with the decoding example. I've done one example in the previous lecture. So we took one particular code word and decoded it, and in fact we also introduced a 1-bit error in that code word at a specific location, and we show that it can be detected as well as corrected. We'll do that with the other combinations of errors, and also introduce multiple errors in the code word and see how the decoding process works. So for the decoding process, we use the parity check matrix, right? Parity check matrix, which we denote as the H matrix. So the H matrix for the 7/4 Hamming code has the form 1 1 1 1 0 1 1 1 0 and 0 1 1. That's the parity matrix part, and then at the bottom the last three rows of this matrix are just an identity matrix, which is 1 0 0 0 1 0 0 0 1. So this is our parity check matrix, or the H matrix. So we call this as the H matrix. To perform the decoding, what do? We take any the receiver or the decoder would multiply the received code word with this parity check matrix and get what is called as the syndrome. Okay, so it computes a syndrome. S is equal to the code word multiplied by the H matrix. So let's take the same example which we did in the last lecture, and the code word we used in the last lecture is 1011 1011 010. Okay, this is the code word which does not have any errors in it. This is the original code word without any errors, and when we multiplied this with the parity check matrix, we got the syndrome S here to be 0 0 0. So when the syndrome is all zeros, it means that there is no error, so the decoder will accept this as a valid code word. Okay, so we've done this already in the last lecture. Then what we also did in the last lecture is we introduced an error in the fourth position. So the fourth position we changed from 1 to 0. We deliberately introduced an error and made this 1 as 0, and then we computed the syndrome by multiplying with the parity check matrix. And when we did that, we got the syndrome value as 0 1 1, which is 0 1 1. So that's the answer we got when we multiplied for this particular code word, which has an error in the fourth position, and we got the syndrome as 0 1 1. Now the decoder looks at this syndrome and compares it with the rows of the parity check matrix. It checks which one the syndrome matches with. So when you look at the row with which it matches, you can clearly see that the syndrome value S is the same as the fourth row of the parity check matrix. So that means there is an error in the fourth position of the code word. And obviously the correction process is done by using a mapping table or a lookup table, right? So the lookup table, let me do that also. So we have a lookup table. So the lookup table contains all the possible syndromes, which are 1 1 1. There are 7 rows of the parity check matrix. So the syndrome is going to be either 0 0 0 or one of the 7 rows of the parity check matrix. If it is 0 0 0, then there is no error, so we do nothing about it. But if it is anything other than 0 0 0, then we are going to have to fix the error. So the lookup table will contain all the possible syndromes, which is 1 1 1, 1 0 1, 1 1 0, 0 1 1, and 1 0 0, 0 1 0, 0 0 1. So that is the syndrome. So the lookup table has a column denoting the syndrome, and then it has another column called the error vector. The error vector, if it is 1 1 1, it is the first row of the parity check matrix, so it has a 1 in the first position, and the remaining 6 positions would be zeros. Similarly, for the second row, it is a 1 in the second position, and all the others would be 0. 0 0 1 0 0 0 0. So the 1 is in the third position here. For this one, the 1 is going to be in the fourth position. For this, it is going to be in the fifth position, and here in the sixth position, and here in the seventh position. So we have these error vectors. So what the decoder does is, after computing the syndrome, it compares the syndrome value in the lookup table and finds the corresponding error vector, and it will simply add the received code word with the error vector. So the received code word that we have here is 1010 So 1010 that gets added modulo 2, which is the same as the XOR operation, with the error vector corresponding to the syndrome that we have computed. So the error vector corresponding to the syndrome is this error vector E, which is having a 1 in the fourth position. So it adds that 0 0 0 1 0 0 0. So when you do modulo 2 addition for this, 1 0 1 0, no, that's 1 0 1 1 0 1 0. So you got back the correct code word. So there was an error here in the fourth position. So there was an error in this position, which after the decoding process, where we have multiplied the received code word with the parity check matrix, then obtained the syndrome, and from the syndrome we obtain the error vector and add the error vector to the received code word, and what you have is the correct code word. So now this has been corrected. So the error which was present here has been detected as well as corrected. So let us now do another example where instead of having the error in the third position, let us make it in some other position to illustrate how this works. So let us make the error now, let's say in the second position. Okay, we'll correct this fourth position, which should be 1. Oh, let me change the ink color. So the original code word is 1011 Now let us introduce an error in the second bit. So let's change this the 0 in the second position and make it as 1. So we'll introduce an error here in the second position now. So I'll make the 0 as 1. So now we know that there is an error in this position. So now let us compute what is the syndrome value. So the syndrome value, we multiply this with the H matrix. So multiply this row with the first column of the H matrix bit by bit and add them modulo 2. So 1 into 1 is 1, 1 into 1 is another 1, so that's 2, 1 into 1 is another 1, so that's 3, 1 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 0 into 0 is 0. So we have a total of 3 here. So 3 modulo 2 means 1. So odd number. So modulo 2 addition, if it's odd number, you will get the answer as 1. So the first bit position in the syndrome is a 1. Next we'll do it for the second column of the H matrix. So multiply the code word with the second column bit by bit and add them. So 1 into 1 is 1, 1 into 0 is 0, so 1 plus 0, 1 into 1 is 1, so that's another 1, so the total is now 2, 1 into 1 is also 1, so that's another 1, so the total becomes 3, 0 into 0 is 0, 1 into 1 is another 1, so the total is now 4, 0 into 0 is 0. So 4 modulo 2, so the total we added up to 4, modulo 2, since 4 is an even number, modulo 2 will give you a value of 0. So what you get here is 0. And then we do the same thing for the third column. We multiply the code word with the third column of the H matrix. So 1 into 1 is 1, 1 into 1 is another 1, so 1 plus 1 is 2, 1 into 0 is 0, 1 into 1 is 1, so 2 plus 1 becomes 3, 0 into 0 is 0, 1 into 0 is 0, 0 into 1 is 0. So we have a total of 3, and 3 modulo 2 will become 1. So we get this, the syndrome, as 101. So if you notice now, the syndrome matches the second row of the parity check matrix. So clearly the error is here in the second position. So the syndrome that we get matches the second row of the what do you call it, of the parity check matrix, that is. All right. So next, what the decoder will do is look up this syndrome in the lookup table. So the syndrome is 101. It will look up for the syndrome and take the corresponding error vector and add this error vector to the received code word. So our received code word, what we have received, is 1111010. So it takes the received code word 1111010, and to that it will add the error vector corresponding to the syndrome, which is this error vector, which has a 1 in the second position. So it's modulo 2 addition, or XOR. So 0 1 0 0 0 0 0. So when you add this, you get 1 0 is 1, 1 plus 1 is 2, 2 modulo 2 will become 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 0. So now again you see we had an error in the second position. This was an error, right? So this was an error. It should have been 0. We introduced an error and made it as 1. All right, we made this as 1. The original value was 0. So now that error which was introduced has been detected and corrected now. So now we have the correct code word, which is 1011010. Okay, so clearly we can see that with these two examples we have illustrated that the 1-bit error can be detected as well as corrected by the Hamming code. Now let us make the errors to be 2 bits, okay, rather than we have seen 1-bit errors but in 2 different positions. We have seen an example for the error in the 4th position and an example for the error in the 2nd position, and we clearly see that the decoder works, or the Hamming code works in this case, right? Now let us illustrate this by introducing 2-bit errors, and what we are going to see is, because the minimum Hamming distance is 3, it can detect 2-bit errors for sure, but it cannot correct it, because the maximum number of errors that can be corrected is only a 1-bit error. So if we introduce 2-bit errors, we will notice that it can detect the error but it cannot correct the error. So let us now introduce 2 errors. So we already have an error now in the 2nd position, and we will reintroduce the error in the 4th position which we had earlier. So let me change this 4th position again to be an error and make it as 0. So okay, so let me write the error bits as in red. So we have an error now in the 2nd position as well as the 4th position. Now we will compute the syndrome and see if it is able to detect the error. So if the syndrome is not 000, that means the code is able to detect the error. So let us see if we get something which is a non-zero vector for the syndrome when we multiply this. Okay, so let me first erase this syndrome, and okay, let's multiply it bit by bit. So 1, so we multiply this vector with the first column of the H matrix bit by bit. So 1 into 1 is 1, 1 into 1 is 1, so that's 2, 1 into 1 is 1, so that's 3, 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 0 into 0 is 0. So we get the total is 3, which is odd number, so therefore the bit is 1. So modulo 2 addition for an odd number would give you 1. Now we repeat the same thing with the second column of the parity check matrix. So 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1, so that's 2, 0 into 1 is 0, 0 into 0 is 0, 1 into 1 is 1, so that's 3, and 0 into 0 is 0. So we have a total of 3, modulo 2 will make it as 1, right? So 3 modulo 2 is 1. Okay, and now for the third column, the operation with the third column, 1 into 1 is 1, 1 into 1 is also 1, so that's 2, 1 into 0 is 0, 0 into 1 is 0, 0 into 0 is 0, 1 into 0 is 0, and 0 into 1 is 0. So we have a total of 2. So total 2 means modulo 2 addition will give you 0. So you'll get it as 1, 1, 0. So what you notice now is clearly it is not 0, 0, 0. Therefore, it is able to detect the error. Since the syndrome, in this case, okay, since syndrome S is not equal to 0, 0, 0, the error is detected. But can it correct the error? Well, it depends. Let's see. Obviously, for this particular code, based on the minimum Hamming distance, we know that this particular code cannot correct 2-bit errors. Okay, so it can detect the errors, which is clear. It has detected it because it's not 0, 0, 0. But if it tries to correct it now, it will try to look up the table for 110, and 110 is in the third row. So now the decoder thinks that the error is in the third position, but the third bit is actually a correct bit. So if it tries to change this bit, it is going to make the 2 errors into 3 errors. So it cannot correct this error. If it tries to correct this error, it is going to make the problem even worse. So instead of 2 errors, it is going to increase the number of errors rather than decreasing the number of errors. Instead of fixing the problem, it is going to create more problems. Why? Because you are asking it to solve a problem which is beyond its capacity. It is able to solve only maximum of 1-bit errors. But if you ask it to solve 2-bit errors, it fails and it causes more problems by introducing additional errors in the process. So let's see what happens. Okay, if we just proceed with the normal procedure, so the decoder will take the syndrome. Okay, and what is the syndrome we had here? The syndrome is 110. So corresponding to 110, it looks at the error vector and adds that error vector to the received code word. So the received code word we have here is 1110010, right? So the received code word that we have is 1111010. So that's our received code word, which has an error in the second position and in the fourth position. So there is an error in the second position, which is here, and the fourth position, which is here. But based on the syndrome, it finds that the error vector is corresponding to 110 is having a 1 in the third position. So it adds that particular syndrome. So modulo 2 addition 0, 0, 1, 0, 0, 0, 0. So when you add that, what you get, 1 0 is 1, 1 0 is 1. So that has not got fixed. It is still an error. 1 1 is 0. The third bit was actually having no error, but in trying to fix the error, the decoder is now introducing a new error. So again, that has gone wrong. 0 0 is 0. That still remains wrong. 0 0 is 0, 1 0. So those are okay. Now the errors which were present originally are still there, but in trying to fix those errors, the decoder has now introduced a third error, which is here. So it has made the problem even worse. Previously the received code word had only 2 errors, but now the decoder has introduced another error and made it 3 errors. Okay, why? Because it is beyond the capability of the decoder, because the decoder for this particular or the Hamming code is designed to fix a maximum of 1 bit error. It can correct a maximum of 1 bit error. Of course, it can detect 2-bit errors. So it is able to detect the error because the syndrome is not 0 0 0. But if it tries to correct the error now, it causes more problems. It increases the errors from 2 to 3. So there are now 3 errors in the process. Okay, so there is a limit, and that limit of the error detection and correction capability is given by the minimum Hamming distance. Now let us introduce one more error and make it a 3-bit error, but we will now make the 3-bit error in such a way that the 3-bit changes results in another valid code word. Okay, let us work on that, and I will show you an example by taking a code word and another code word which are 3 positions apart, and then we will demonstrate that with 3-bit errors the decoder fails to detect the error. Okay, because the maximum number of errors that can be detected with guarantee is 3-bit errors. So let's take 2 examples here. From our list of code words, I am going to take 2 particular code words, which is, let me erase this one. So we'll erase this particular code word now, and let's take the code word number 2, which is 0 0 0 0 0 1. No, not this one. Let me rewrite that with a different ink. Let's say 0 0 0 1 0 1 1. So that's one code word, and another code word that we are going to take is 0 0 1 0 1 1 0. Okay, if you compare these 2 code words, what is the Hamming distance between them? That's 0 or 0, that's same, that's 1-bit position, that's 2-bit position. That's 4. Now let me take another example. Okay, suppose we take these 2 particular code words, and you see that the Hamming distance between them is d is equal to 3. So the number of bit positions in which these 2 code words are different is 3. So these 2 bits are same, these 2 bits are same, the third position is also same, the fourth position is different, so that's 1 difference. The fifth position is same, sixth position is different, so that's 2 differences, and the seventh position is also different. So the distance between these 2 code words is 3. So suppose now that we transmit one of these code words. So let's say we transmit the code word here, which is 0 0 1 0 1 1 0. Suppose that is what we transmit, 0 0 1 0 110. So suppose that is what we transmit, but the channel introduces errors, and suppose that the errors occur in the fourth position. So the fourth bit, which is 0, suppose this becomes 1. The sixth position, which is 1, that becomes 0, and the seventh position, which is 0, becomes 1. So let's change these 3 bits and convert this particular code word into another code word and see if these errors are detected or not. So let's introduce this error. So the 0, we make it as a 1. This 1 over here, we make it as a 0, and the 0 over here, we make it as a 1. So now what we transmitted is this code word 0010110, but there are 3 errors in this code word, which has converted this code word into another valid code word from the list of code words. So what the receiver has got is 0011101. So the receiver does not know where are the errors. Okay, we have introduced it, we are able to see it, but when the receiver gets such a code word, it doesn't know where the errors are or whether there are errors or not. It has to do the process by multiplying with the parity check matrix, compute the syndrome, and look up at the lookup table, and then try to correct the error. But in this case, let us compute the syndrome and see if there is any error or not. So let's compute. 0 into 1 is 0, 0 into 1 is 0, 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1, so that's another one. So 2, 0 into 0 is 0, and 1 into 0 is 0. So the total we got is 2, and 2 modulo 2 is 0. So the first bit of the syndrome is 0. Similarly, now let us do for the second column of the H matrix. 0 into 1 is 0, 0 into 0 is 0, 1 into 1 is 1, 1 into 1 is another one, so that's 2, 1 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0. So the total we got is 2, and 2 modulo 2 is 0. And we do the same thing for the third column now. So 0 into 1 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1, 1 into 0 is 0, 0 into 0 is 0, 1 into 1 is 1. So 1 plus 1 is 2, so modulo 2, so that is also 0. Now clearly what is happening here is the receiver, the decoder, gets a syndrome value which is equal to 0, 0, 0. So therefore it thinks that there is no error at all, because the syndrome is 0, 0, 0. Since the syndrome is 0, 0, 0 in this particular case, the error is not detected. So in this particular case, the decoder fails to detect the error. The error is not detected. Right? Why it is not detected? Because one code word that you transmitted has got changed into another valid code word from the list of code words that we generated. So the decoder now fails to detect the error, and the reason is because the minimum Hamming distance tells us that it can detect a maximum of 2 errors with guarantee. If it is more than 2 errors, maybe sometimes it is able to detect it, but sometimes it may not be able to detect it. When will it not be able to detect it? When one code word gets changed to another code word. In that case, it will give the syndrome as 0, 0, 0 and accept it as a valid code word. Okay, so we have seen the case here when the error detection also will fail. Okay, so the minimum Hamming distance is an indicator as to how many errors the particular coding scheme can detect and correct, and in this case for the Hamming codes, the minimum Hamming distance is 3, and therefore it can detect a maximum of 3 errors. The maximum of d min minus 1, which is 3 minus 1, that is 2 errors, and it can correct a maximum of 1 bit error. Okay, and we have illustrated this with a few examples. We have seen a 1 bit error which it was able to detect as well as correct, 2 bit error which it was able to detect but it could not correct it, and now we have seen an example of 3 bit errors which are not even being detected. So there are 3 errors clearly here, which we know we introduced those 3 errors, but the decoder has not detected those errors because it gives a syndrome value s equal to 0, 0, 0, and therefore the error is not detected. Okay, so that's to do with the 7/4 Hamming code. Now the other thing I want to continue now is, in addition to the 7/4 Hamming code, what are the other values of n and k that we can have for the Hamming code? Okay, the design of Hamming code is such that the minimum Hamming distance is always 3, and with a minimum Hamming distance of 3, what are the numbers that you can have for n and k? In this case, n is equal to 7 and k is equal to 4. So what other values can you have? We can't choose those values arbitrarily as we like. There is a particular rule that we have to follow to get those numbers. So I'm going to illustrate that now. So what are the possible values of n and k for the Hamming code? So values of n and k for Hamming codes, okay, which have a minimum Hamming distance with 3. So with d min equals 3. So how do we choose the values of n and k? Well, the rule is that you choose the value of n to be equal to 2 power, let's call it m, 2 power m minus 1, and the value of k that you can choose is 2 power m minus 1. So this is how you would choose the value of n and k for the Hamming code. And what is this m? Where m is an integer which is greater than or equal to 2. So m should be a value which is greater than or equal to 2. So we can have it as 2, 3, 4 for m. For the value of m here, we can have it 2 and any other value, and integer value above 2. And let us see what happens, what are the numbers we get for n and k for different values of m. So let's say we start with the smallest value of m possible, which is 2. For m equal to 2, we get n is equal to 2 power 2 minus 1, which is 3, and k is equal to 2 power 2 minus 2 minus 1, which is 4 minus 2 is 2, minus 1 is 1. So we get nk is, it will be a 3-1 code. Okay, so 3-1 Hamming code. What is the code rate for this? The code rate is k by n, which is 1 by 3. So the code rate is 1/3. That means in a code block of 3 bits, 1 bit is the information bit and the remaining 2 bits are the parity bits or the protection bits. So the coding efficiency is 1 by 3 into 100, which is like 33.3%. So let's do that for m equal to 3. For m equal to 3, what do we get for the values of n and k? So n is equal to 2 power 3 minus 1. So that's 8 minus 1, which is 7. and k is equal to 2 power 3 minus 3 minus 1, which is 8 minus 3 is 5, minus 1 is 4, right? So we have 7 4, which is what we have been discussing all this while. So what we have here is a 7 4 code. So for the 7 4 code, what is the code rate? It is 4 by 7, okay, which is slightly over 50%, right? 4 by 7 is, okay, let me write the efficiency, which is say 33.33%. So in this case, what is the percentage value in terms of the efficiency? So 7, it is 7 5s are 35, 7 7s are 49, 57, 1 3, okay, it's something like 57.14%. So for m equal to 3, we have the code rate, which is 4 by 7, that is, the coding efficiency is like 57.14%. Let us do it for m equal to 4. So for m equal to 4, what do we get? M equal to 4. So in that case, n is equal to 2 power 4 minus 1, that is 15, and k is equal to 2 power 4 minus 4 minus 1, so that's 11, right? So we get the nk code as 1511 code. So the code rate is equal to 11 by 15, okay? And how much is 11 by 15 in terms of the coding efficiency? So 11 by 15 is 73.33%, okay? And similarly, you can do it for m equal to 5, 6, 7, and so on. And what you notice is, as you increase the value of m, okay, as you increase the value of m from 2 to 3 to 4, and you're going to go to 5 and so on, what you notice is that the coding efficiency, or the code rate that you get, approaches 100%, okay? The code rate approaches 1, or the efficiency approaches 100%. So when m equal to 2, your efficiency is 33%. When m equal to 3, the efficiency is 57%. When m equal to 4, the efficiency is 73%. And when you do for m equal to 5, let me do that also. For m equal to 5, you'll get n is equal to 2 power 5 minus 1, which is 2 power 4, 32 minus 1, which is 31, and k is 2 power 5 minus 5 minus 1, so that's 31 minus 5, right, which is 26. So the nk code here is 3126 code. So the code rate r is equal to 26 by 31, k by n. So that's 26 by 31. So what do we get for 26 by 31? 26 by 31 is 83.87%, right? 83.87%. So you see very clearly that the code rate R is getting closer and closer to 1, and that means the coding efficiency is getting closer and closer to 100% as we increase the value of m. Okay, so but the minimum Hamming distance for all these codes will remain 3, and for that minimum Hamming distance of 3, these are the maximum efficiencies that you can achieve with the Hamming code. So if you want to increase the efficiency and hence the code rate, that means you need to increase the block length. Okay, so the block length from 3 you have to go to 7, so n is the block length, right? So if you want to improve the efficiency, the block length, you go from 3 to 7 to 15 to 31. So if you have a bigger and bigger block length, you have a bigger and bigger coding efficiency, or the code rate approaches 1. So what we notice here is that as m is increased, the code rate of Hamming code approaches 1. Okay, and which is what we want to do. We want to have a code rate which is as close as possible to 1, because that would mean as little extra bits as possible for the protection. That is the design objective of the coding scheme. But again, that has two consequences. If you keep on increasing the block length, that means you are making the code more and more complex in terms of the computations. Okay, so the as the value of m is increased, the code rate approaches 1. That is, the coding efficiency approaches 100%. So we have a coding efficiency that is close to 100% as we increase the value of this m. Okay, so these are the possible combinations that you can have for n and k for a Hamming code. Okay, it can be a 3-1 code or 7-4 code, and we have seen the 7-4 code in quite a bit of detail, and it can otherwise be a 15-11 code or a 31-26 code, and so on. And accordingly, we need to construct the generator matrix and the parity check matrix for these values of n and k, and then perform the encoding and decoding, and then we get the error, the detected and corrected values of the bits, right? So depending on the number of errors, it can detect a maximum of dmin minus 1 errors. Dmin minus 1 errors can be detected, and the number of errors that can be corrected is the floor value of dmin minus 1 by 2. Okay, so that brings us to the end of this topic of the Hamming codes. I will continue with the next topic in my next lecture, and I will now open the session for any questions that you may have, and we can discuss any queries that you have. All right, thank you guys. We'll start the discussion session now.